For a number of years, Alyosha Efros, a prolific computer vision researcher, has claimed that for all the successes of supervised deep learning to date, there is one thing we can be sure of: the revolution will not be supervised. Instead, once we really start scaling things up, self-supervised learning will win the day, and self-supervised learning is the topic for today's video. We'll look at the motivation behind self-supervised learning and some of the influential approaches that have been taken to date. Let's begin with the motivation for self-supervised learning, starting with a summary of the state of the nation for the nation of machine perception. We have a number of reasons to be cheerful. Deep learning has given us remarkable progress with the supervised learning paradigm, in which we gather a large collection of data and manually annotate it, and supervise a model with the resulting annotated data. This has yielded truly major gains on vision benchmarks. Of course, benchmarks are not the goal in themselves, and they have drawbacks. They can trap you into a local minimum of research ideas, for example, but they have clear value in allowing an objective comparison of different methods. Still, we have some cause for concern, and somehow it seems that we still have a long way to go. Even the highest capacity models trained on the largest annotated datasets continue to make what we might call silly mistakes that would never be made by a human. Perhaps more worryingly, it seems that we can just never get enough labeled data to get close to the human perception system. This state of affairs prompts a natural, age-old question. Can we take inspiration from the early stages of development of human perception to improve things? To answer this, it's worth considering the wealth of research that has studied human development in some detail. Human baby learning is incremental. A child learns in a continuously evolving environment, rather than a stationary distribution. It is social. Babies learn from other humans around them, particularly caregivers. Physical. They offload knowledge to the physical world around them and store information with respect to their surroundings. Baby learning is exploratory. Once their curiosity is aroused, they try a lot of things to find something that works. Learning is language-based, allowing them to not only communicate, but also learn abstractions that support generalization. Finally, their learning is highly multimodal, experiencing sensations from sight, sound, touch, taste, proprioception, balance, and smell, when these senses are available. Different modalities provide significant redundancy among their inputs to learn from. It's also interesting that babies naturally build curricula for their learning. Careful analysis of the appearance of objects observed by babies shows that they follow a strong power law. A small number of objects are seen an incredibly large number of times, such that the child becomes an expert in recognizing and manipulating those objects. If you have good eyesight, you may be able to spot the baby's favorite green sippy cup appearing frequently among these sample images. Okay, this all sounds great, and many people have observed that our current machine perception systems are doing very little of these human-inspired learning strategies. Why is that? I would say that the main barrier to implementing the kind of embodied perception learning exhibited in babies has been practical. In fact, this challenge was noticed by Alan Turing, who was interested in the development of such machines, and observed in 1948 that, in order that the machine should have a chance of finding things out for itself, it should be allowed to roam the countryside, and the danger to the ordinary citizen would be serious. The takeaway here is that there are some practical challenges to embodied learning, which is the general term given to an agent possessing a body that learns to interact with its environment. It's possible that recent developments in simulation may help us here, but we are still some way off from recreating the world in sufficient fidelity to have fully addressed this problem. For that reason, we will talk about a family of methods that tries to make progress principally on perhaps the safest of the human learning characteristics, multimodal learning. In particular, we will discuss self-supervised methods that are partly inspired by human multimodal learning in the sense of exploiting redundant signal. The essence of self-supervised learning, as you might infer from the name, is that the learner should create its own supervision. This is an old idea that was nicely articulated by Helmholtz in his legendary 1878 speech on the facts in perception. Each movement we make by which we alter the appearance of objects should be thought of as an experiment designed to test whether we have understood correctly the invariant relations of the phenomena before us, that is, their existence in definite spatial dimensions. So we can create a plentiful supply of learning targets by simply moving and checking whether our model of the world was able to predict what we will see. The role of redundancy in sensory signals was then considered more explicitly by Barlow, who made the observation that learning requires previous knowledge. In particular, To detect a new association, such as that event C precedes event U, we need to know the prior probabilities of C and U. If we have those, then we can learn a new association if we observe that C is followed by U more frequently than would be expected by chance. The key role of redundancy is that in order to know what usually happens, we need redundancy in the input signal, which could be, for example, sensory messages of the same event from different modalities. The redundant signal is, by definition, the part of the signal that can be predicted from the remaining signal. This redundant signal provides labels for training a predictive model. One computational trick that is nicely illustrated in Barlow's work relates to the kinds of codes we use to represent events in our environment. The observation is the following. To test whether two events are co-occurring more frequently than would happen by chance, we need to know their prior joint probabilities. So, when learning pairwise associations between n events, we need to store n² co-occurrence probabilities. But if we've learned representations in which events C and U are statistically independent, we can compute the chance co-occurrence of C and U from the product of their marginals. That means we only need to store n event probabilities. This can help to avoid a combinatorial explosion of storage for prior event probabilities. Barlow himself suggested minimum entropy coding as a scheme to obtain factorial representations, but this idea applies more generally. It's always desirable to achieve this independence property where possible. One of the first works to use the term self-supervised that operationalized this insight about learning from redundant signal was proposed by Virginia Dessart in the 1990s, who helpfully provided an intuitive bovine-based explanation. In supervised learning, each time we see an image of a cow as input, we are provided the corresponding cow label. But it is implausible to collect all labels required for such a task. Unsupervised learning takes in the same cow image and seeks to learn a powerful representation of it without labels. In the self-supervised approach proposed here, labels are derived from co-occurring inputs across modalities, providing redundant signal. Learning then proceeds by minimizing the disagreement between class labels predicted from each modality, rather than matching predictions against an external annotation set. This is an idea that underlies a number of modern approaches. It's also worth noting that in the modern literature, the distinction between self-supervised and unsupervised learning, as given here, can become a little blurry. A general way to think about the redundancy found in multimodal signals is that the redundancy comes from the context surrounding a piece of information. In the natural language processing community, unlabeled text corpora have been used for a long time to provide low-level supervision for neural networks, with the hope that the distributed representations learned by these models will enable them to generalize. One example of such models are autoregressive models, in which the joint probability of a sequence is factored into a product of conditional distributions, with each element in the sequence conditioned on the previous elements. Then, a network can be trained to maximize the likelihood of a text corpus under this factorization. For example, a network can be trained to predict the next character in text to enable compression, or to predict the next word to learn a language model. A slightly more adventurous use of context was explored by the word-to-vec skipgram model, which was trained to predict the collection of words surrounding any given word in the corpus. This is simple to train without labels. You simply pick a word in a sentence, mask its neighbors, and then try to predict those neighbors from the current word. This work was really a breakthrough in terms of language modeling performance, and highlighted the critical importance of having lots of training data in getting good word vectors. More recently, various multitask masking schemes have been considered. Perhaps the best known is BERT, which was trained to predict randomly masked words in a sequence in addition to predicting the next sentence in a corpus. This work showed, amongst other things, the benefits of using a high-capacity transformer for language modeling. It's perhaps a little less obvious how the same approach can be applied to computer vision. The strategy that has been developed has been to train a neural network by tasking it with playing a game, which is often referred to as a pretext task. Now, typically we don't care about the performance of the model on the pretext task itself, but we hope that by solving it, a model learns good representations of the visual world. Work by Autoencoders and colleagues illustrates this idea nicely. A network is shown two image patches. These image patches have been cropped from nearby regions in the same image. The pretext task for the model is to guess the relative position of the red dashed crop to the blue crop. Here's an example. Ask yourself, where does the red dashed crop belong relative to the blue crop? If you guessed bottom right, you are correct. But how did you solve this task? You recognized it was a bus? Then you used your knowledge of buses. In fact, you've probably never seen this particular bus before, but you could still do it. Here's a second example. Where does the red dashed crop belong relative to the blue crop? Take a guess. If you guessed top center, you are correct. Again, how did you solve the task? I'll assume you've never seen this train before, but you have robust recognition. The key idea is that a model can only solve these questions once it learns to recognize novel instances of cats, buses, and trains, and develop some understanding of their structure. Importantly, no labeling is required to construct this task. This seems like a cute idea, and it is, but a warning is needed. Sometimes the model won't solve the task in the way that you wanted. In this work, Dersch et al. Found that the network can learn to cheat by exploiting a low-level signal, the chromatic aberration that results from a camera lens focusing light differently at different wavelengths. One color, typically green, is shrunk toward the image center relative to the others. Once the network has figured this out, it can solve the problem trivially by determining the absolute locations of the patches relative to the lens, without learning anything at all about cats, buses, trains, or the host of other interesting objects we'd like it to know about. The authors solved this problem by randomly dropping color channels from each patch, so the network could not rely on this cue. But still, it provides a cautionary tale. Constructing pretext tasks requires a lot of care. In fact, this problem, related to an idea known as specification gaming, is also a major problem for AI safety, for those who are interested in this topic. Partly because it works quite well, and partly because it's a fun research problem, researchers have come up with a number of creative pretext tasks for training deep neural networks. One example is training a network to inpaint by removing patches of images and requiring the model to fill them in. What this means is that we start from an image with a section removed, and we train the model to inpaint it. The great thing about this is that we can set up a model to perform this task without any labels. We just randomly crop bits out of images for supervision. One thing that's somewhat unusual about this particular pretext task is that it is actually useful. Inpainting is used by digital artists and designers, for example. There are some nuances to getting this to work well. The authors use a loss that contains two terms. The first is an L2 loss on patch reconstruction, which looks like this, where P is a vector of pixel values inside the patch. This works, but it has a problem. It produces blurry predictions because the model is encouraged to hedge its bets. They therefore use a slightly more complex adversarial loss inspired by generative adversarial networks, which looks like this. This loss involves training a second whole network, called the discriminator, jointly with the main model. One term in the loss encourages the discriminator to be able to recognize real patches from images, while a second term encourages the main patch predictor model to fool the discriminator. Empirically, this kind of loss can significantly reduce blurriness and improve inpainting. However, it is a headache to train. The main useful result from this paper was that the encoder is ultimately able to learn useful features for classification, detection, and segmentation, which is a great outcome given that no labels were used. However, this was done with only the L2 loss, simply because the authors had too many issues with getting the adversarial loss to work in all settings. The next creative pretext task is learning from jigsaws. Everyone likes jigsaws. The idea is that you can start from an unlabeled image and overlay some grid of boxes. Then you can randomly shuffle the patches under the boxes and train a network to solve the resulting jigsaw puzzle. The way that this is implemented in practice is we sample a training image and a random permutation from a collection. Then, the patches are permuted and passed into a network similar to AlexNet, which is trained to predict the permutation label. What's great is that the features used by the network can then be used for tasks like image classification and image retrieval. Another nice piece of analysis in this work visualized some activations to see what the network was learning. Here are some top-firing activations for filters in conv1, which you can see has learned low-level features like edge detectors and grids. If we move higher up the network to the fourth conv block, we see the emergence of part detectors for things like dog faces and legs, similarly to what we'd expect to see from supervised learning. Our next pretext task is learning from colorisation. The idea here is that we can first remove the colour from images like this, then train a model to add it back in. The key premise is that the model can only fill in the image with plausible colours if it understands the image content. A key challenge for this approach is that the distribution of plausible colours is inherently multimodal. Take a look at these two images, one of which has been colorized. Which do you think is the original? It's hard to tell. They both look plausible. In fact, both are colorized. The original is a classic black and white photo of a migrant mother taken during the Great Depression. Multimodality represents a problem when using an L2 regression loss, which produces greyish colors. The solution adopted here is to make predictions in quantized LAB space, which decomposes color into perceptual lightness, that's the L, and then two further axes, A and B, that span green, magenta, and blue, yellow. Predictions are made with a cross-entropy loss, rather than regression. The authors then train a neural network to make predictions in this color space by taking the lightness as an input and predicting A and B values. Once the model has been trained on this task, the features can then be used for standard computer vision tasks like classification, detection, and segmentation. As a bonus, the trained model can be used for fun applications like colorizing historical black and white photographs. The animal on the left is a Tasmanian wolf, a mammal that went extinct about 100 years ago. Now, I've mentioned a couple of times that using an L2 regression loss can cause problems. What's wrong with it? For many kinds of machine learning problem, when we are modeling unimodal distributions, L2 regression is a good choice. However, it's very much not a good fit for predicting multimodal distributions. Why is this the case? Well, suppose that our task is to model a single RGB pixel image. This image is pure red with probability 1/3, so its RGB value, assuming we've normalized to 0, 1, is 1, 0, 0. It's pure green with probability 1/3, so its RGB value is 0, 1, 0. And it's pure blue with probability 1/3, so its RGB value is 0, 0, 1. Here's an example of a training set containing 24 samples of our pixel, with equal proportions of each color occurring. Now suppose we train a model to predict samples from this training set using an L2 loss. We'd like a model that reproduces instances that are highly likely under the true model of the data. Unfortunately, that's not what will happen. Take a moment to think what the model will predict. It will predict the average value, which here is to put 0.33 in each position. Samples from the model will look like this, which doesn't match the training distribution at all. This is a toy example, but hopefully it gives you some intuition why colorization with an L2 loss can produce grey-looking pictures. The model has to average over plausible colors. The next pretext task is learning by counting. This is an ingenious idea. Suppose you have an image like this. Now, let's also suppose that we've already learned a really useful vision model that can count dog-related concepts in the image, such as dog noses, dog eyes, paws, and heads, etc. If we had such a model, and we trusted it, we could divide the image into 4 quarters and run our counting model on each quarter separately. In the top left quarter, we should get 1 nose, 2 eyes, and 1 head. In the bottom left quarter, we should get 3 paws. In the bottom right quarter, we'd get 1 nose, 1 eye, 3 paws, and half a head. And in the top right, we'd get 1 eye and half a head. Now the magic here is that if we reran our trusted counting network on the whole image, we should get 2 noses, 4 eyes, 6 paws, and 2 heads. And importantly, this should match the sum of the counts across the 4 quarters. The fact that the sum should match gives us a consistency constraint that we can use for training. How this is implemented in practice is that during training, we sample an image, choose a crop, then split it into 4 quarters. We pass each of these 4 quarters through our counting network and sum the resulting vectors. Then we take the full image crop and pass that through our network as well. To enforce consistency, we use an L2 loss to encourage the full image counts to match the sum of the 4 parts. This seems very cute, and it is, but there is a problem. The model can find a so-called trivial solution that solves this loss perfectly. Take a moment to think what this solution might be. It can just predict a count of 0 for every image and concept, which will perfectly satisfy the consistency loss. The solution adopted by the authors is to use contrastive images that stop the model from being able to always predict 0. This is done by randomly sampling another image during training, passing it through the network, and then using a margin loss to ensure that the counts for this image are different to the other images. So predicting 0 everywhere will incur a significant loss here. One point to note here is that the concepts that actually get counted are not specified directly. They could be noses and eyes and paws, or they could be something different. The model gets to choose what to count, and it will choose whatever helps it satisfy the loss. The authors show that features trained with this counting loss form a strong basis for classification, detection, and segmentation. Before describing our next pretext task, we need a little bit of background terminology from psychology. In the early 20th century, the Gestalt school of psychology emerged as a paradigm for understanding various aspects of human thought. One of the major contributions of this school was to propose several grouping principles to help explain human visual perception. Now, there are many such principles. The one we are interested in here is called the principle of common fate. Here's an example of it in action. Even though this is just a bunch of dots moving on a white background, we perceive 5 of them as belonging to the same object. More broadly, we perceive visual elements that move with the same velocity as being part of a single whole. Our next pretext task exploits this principle as a self-supervision signal. In particular, the key idea is that pixels that belong to the same object are much more likely to move together than pixels that do not. Just as we saw with counting, this gives us a consistency constraint that we can turn into a loss function. If we had a model that could already understand an image and segment it into objects, then we can enforce that the pixels on those objects move together. To turn this into something concrete that can train a model, the authors start by selecting a video clip from a training set. Then, they pluck out one image from the sequence and pass that image to a CNN, which is used to extract embeddings. In parallel, they take both the current frame and the next frame in the video and use them to extract optical flow. For those who have not encountered this previously, optical flow is a 2D vector field where each vector is a displacement vector showing the movement of points from one frame to another. It's quite a low-level feature that is not too hard to estimate roughly. Now, here is the key part. They compute the similarity between all the pixel embedding vectors, and they also compute the similarity between all the optical flow vectors. Then they feed both of the resulting similarity matrices into a loss function that tries to make them as similar as possible. What this does is encourage the network to learn embeddings of pixels that move together. As a result, the network learns to segment objects, at least to some degree. And as for the other methods, the main benefit is that we can use the features learned with this loss for tasks like classification, detection, and segmentation. The next task exploits a simple but powerful bias that is present in a great deal of online imagery. That bias is that humans tend to take photos the right way up. As a result, if images are rotated anti-clockwise by 0 degrees, 90 degrees, 180 degrees, or 270 degrees, we can spot that a rotation has been applied. As a proof of concept, try pausing the video and checking if you can guess the 5 anti-clockwise rotations that have been applied to these images. The answers are 90 degrees, 270 degrees, 180 degrees, 0 degrees, and 270 degrees. Okay, how did you achieve this? By understanding the image content. We can turn this into a self-supervised method by sampling an image and then applying rotations of 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Then we feed each rotated image into a convnet and train it to predict which rotation was applied. Although it is among the simplest methods, in practice, rotations work extremely well and produce very strong features, which the authors show through various experiments. They also conduct some nice analysis to show that if you compare the first layer filters for AlexNet produced by supervised training and self-supervised training, they end up looking surprisingly similar. So somehow this simple objective is indeed causing some effective learning to take place. Up until this point, we've discussed a number of methods that have a highly intuitive feel to them. In some sense, there is a simple story for why they work. Some of the best performing methods, however, don't have this property. An example is learning from clustering. The method itself is very simple. We start from an unlabeled collection of input images. We pass them all through a convnet to compute features, and then we do something curious. We run k-means clustering on the features, typically with a fairly large value of k. Then we take those cluster labels and use them as pseudo-labels that we treat as targets for classification, and we train the model with backprop and std to classify the pseudo-labels. And then we repeat this process, alternating between clustering and classifying until somehow the model gets really good at it. And voila, somehow we get out really great features for downstream tasks. It's all rather mysterious. What is going on here? Well, one observation is that, even with random weights, a CNN performs much better than random clustering. What appears to happen is that with each iteration of clustering and classification, the model starts to form more and more meaningful clusters. That's captured here by this clustering quality metric that gradually improves with training. An additional nice piece of analysis the authors do is to visualize the top activated images from the last convolutional layer in the network. They find filters that have learned highly specialized concepts relating to buildings, cars, keyboards, and white fluffy animals. This all points to a network that is learning some interesting things. Another broad family of self-supervised methods that has been developed is based on the idea of contrastive learning with augmentations. There are many such approaches. I'll describe the widely adopted SimClear method from Google as a representative example. SimClear stands for Simple Framework for Contrastive Learning of Visual Representations. A key idea underpinning this approach is to exploit the fact that data augmentations can often preserve semantic meaning. That is, if we start from an initial image and apply various forms of data augmentation, much of the meaning of the image is preserved. In fact, this is the same reason we use data augmentation in supervised learning. What's different in this case is that we couple heavy data augmentation with instance discrimination within batches as a training objective. To create samples for our loss, we start from an image. Then we sample a data augmentation and pass the resulting image through our network and project the result to a lower dimension. We pass the same image through a second transformation and then again through our network and project the result. The loss aims to maximize agreement between projections such that we learn a good representation. How this is actually implemented in practice is with a contrastive loss, where for a positive pair, ij, the loss is given by the negative log of a softmax of the embedding similarity. Here the numerator similarity comes from the positive pair, i.e. the two augmentations derived from the same original image. The denominator is over all pairs that can be formed within the batch, and this loss is computed across all possible positive pairs. At the time of its release, there was particular excitement with this work because it reported results for SimClear, shown with the red stars, that started to really close the gap on standard ImageNet evaluations to supervised learning features, which are shown here in the top left with a grey cross. The final method I'll describe is based on the concept of masked autoencoders and uses the transformer architecture. It is also among the simplest and best performing methods available today. We go back to the pixel patch reconstruction we saw right at the start with inpainting, but this time we will use very high masking ratios, high capacity transformers, and our old friend, the L2 loss. We start from an image, and we mask out 75% of the image, divided up into patches. Then we feed only the unmasked patches to a transformer VIT encoder, which maps them to embeddings. After this, we stitch back in the masked patches and feed them to a lightweight decoder, which produces a set of pixel patches, which can be reshaped to produce the image predictions. One clever aspect of this design is its efficient asymmetry. What we really care about is the encoder, so we'd like to make that as chunky as possible. With this design, the encoder does not need to process the whole image. It only processes 25% of patches. The decoder, on the other hand, processes all the patches but can be made much more lightweight. We talked previously about how the L2 loss does not encourage sharp predictions, and we find here too that the transformer produces quite blurry predictions. Here, the masked input is shown in the left column and the masked prediction is in the middle column, and is pretty blurry, and the ground truth is on the right. One last observation here, nicely highlighted by this work, is that long training schedules are vital to achieving good self-supervised performance. And in fact, this is key for pretty much all the methods we have discussed. You can see here on this graph of linear probing, which is a way to measure feature quality, that even after 1600 epochs on ImageNet, which is a long time, the model is still improving. Thinking back to Rich Sutton's bitter lesson, you can interpret this as a good sign for the method. It seems to be able to leverage additional computation effectively. In the video description, you can find links to slides and references. I hope you have a wonderful day.